Welcome back, everyone. Today we are learning about the dot product. So we're continuing to learn about vectors for the rest of our next unit, Unit 5, and then we'll move on to our last two units. So far we've learned about vector addition, subtraction, and also multiplication by a scalar. Today we're going to learn about how we can define multiplication between vectors. And an interesting note is we can actually define multiplication between vectors in more than one way. So there's two different ways we're going to look at multiplication between vectors. One of them is called the dot product, which is what we're learning today. The other one is called the cross product, which we'll learn in another video. And the notation that we use for vector multiplication is really important. The dot product, if we have two vectors, v and w, the dot product is v, and then we have a dot in between, and then w. So the multiplication we're used to, and that we see more often in high school and higher mathematics, that dot symbol. The cross product has v, and then instead of the dot, we are writing a cross here, or an x, v cross w. So maybe the type of multiplication symbol we were more used to in elementary school, middle school. The notation that we use is really important because this is how we differentiate between these two definitions of multiplication. So we'll learn about the cross product later. Today we are learning about this definition of multiplication, the dot product. First, let's go ahead and define the dot product. So if we have two vectors, v and w, and let's write them out with their components. So let's say v is a1 times I plus b1 times j. W is a2 times I plus b2 times j. Then the cross product between v and w is equal to a1 times a2 plus b1 times b2. So we're multiplying the x components together and the y components together. And an interesting thing to notice is here we have a vector, here we have a vector, so we're multiplying two vectors, but the result or the product that we end up with is actually a scalar. So notice we're just taking the numbers in those components, the values of the components, and we don't have a direction in our product. So with the dot product, we have two vectors and we end up with a scalar. Let's go over a few properties of our dot product. If we have v and we take the dot product with v and w, that's the same thing as the dot product between w and v. In other words, this definition of multiplication is commutative. A few others, the distributive property also works, u times b crossed with w, u, and then we're doing cross product of b plus w is equal to u crossed with v plus u crossed with w. A few others, if you take a vector and take the cross product with itself, you end up with the magnitude squared. And 0 times any vector defined with the dot product between any vector and 0 is 0 because the I and the j components are both 0 with 0. So some of these might seem kind of obvious. For example, commutative. With pretty much every type of operation that we've defined, those operations have been commutative in all of math that we've worked with so far. However, we do have to be careful because we are going to start to see operations that are not commutative. A quick example, and again, we'll see this later on. So just an aside, the cross product between B and W is not equal to the cross product between W and V. So the other form of multiplication that we define for vectors is in fact not commutative. So although these might seem obvious, it still is important to point them out for the dot product. All right, so next I want to take a look at how to find the angle between two vectors using the dot product, or an alternate definition of the dot product. So first up here, we just have one of the properties that we listed earlier. If we cross a vector with itself, we get its magnitude squared. And then I wrote down a few vectors, two vectors down here. We have V and U. So V and U. Theta is the angle between those vectors. And then finally, I drew this other side to kind of like complete a triangle. And this other vector is just V minus U. So not looking at the magnitude right now, we have VU and then V minus U for the other side. I also want us to think about the law of cosines, which we learned quite a while ago. And I wrote up here. So what we're going to do is consider our triangle on the left and use the law of cosines with regards to theta and this side over here, V minus U. So we start off with the magnitude of V minus U. And again, law of cosines is looking at the side length. So we're looking at the magnitude of all of these vectors squared equals the magnitude of V squared plus the magnitude of U squared minus 2 times magnitude of V times magnitude of U times cosine of theta. And now using our property, we're going to be replacing these magnitudes squared with the dot products. Here we have V minus U, dot product between V minus U and itself. Here we have the dot product between V and itself, plus the dot product between U and itself, minus, and we still have 2 times magnitude V times magnitude U times cosine theta. Okay, then if we distribute this left side, so FOIL or area model, we end up with U crossed with U plus V crossed with V, or sorry, the dot product between U and U, the dot product between V and V, and then subtracting 2 times the dot product between U and V equals this entire right side. And then with some simplification, we end up with U dot V is equal to the magnitude of U times the magnitude of V times cosine theta. And again, this right side is a scalar. So the dot product, we end up with a scalar. So here's an alternate definition of the dot product. We take the dot product between two vectors. If we know their magnitudes and the angle between them, we can quickly find the value using this equation. We can also use this equation to find this angle between vectors if we know their dot product and their lengths by moving around and just dividing both sides by those magnitudes. So the cosine of theta, the angle between two vectors, is equal to the dot product between those vectors divided by the magnitude of the vectors multiplied by each other. So we can use this equation to find the angle between two vectors. And here we have our alternate definition of dot product. So we can define it using their components. We can also use their lengths and the angle between them. Next, I want to consider two specific situations. First, we might end up with vectors that are parallel to each other. If two vectors are parallel, then we end up with an angle of 0 between them. So they're going the exact same direction. So when we take the dot product, what happens is we actually end up just multiplying their magnitudes, and that's because cosine of 0 equals 1. So the dot product is just equal to their magnitudes. I also want to consider perpendicular vectors, and we actually have a special word for perpendicular vectors, and that word is orthogonal. So vectors are orthogonal if the angle between them, theta, is 90 degrees. So it's just a specific way to say perpendicular in terms of vectors. Vectors are orthogonal if theta is 90 degrees, and notice that cosine of 90 degrees is 0. So the dot product between two orthogonal vectors or perpendicular vectors is equal to the magnitudes times 0. So it's equal to 0. That tells us that the two vectors are orthogonal if and only if, so going both directions, their dot product is 0. So we saw that if two vectors are orthogonal, then cosine of theta equals 0, so their dot product is 0. We could also see that the dot product being equal to 0 means that either the magnitude of one of them is 0, so looking back up here, either the magnitude of u is 0, the magnitude of v is 0, or we end up with cosine of theta equal to 0. So assuming these vectors have a magnitude, the only result that gives us 0 is cosine of theta being equal to 0, which means that theta is 90 degrees. So looking at parallel and perpendicular vectors specifically.